the body.
Stand by. You're recording.
Like in Tokyo, I used to play soccer when I was a kid. I'm not very good. I would be the one to kick it off the roof. Unless they kick it off the roof. I kind of look like Tokyo. Propose that to the especially the non-engineering ones. Yeah, that's right. God, I hate these kids.
All right, can we start? Thank you. How's everything, guys? Where is the rest of the gang? Nobody knows? Is there a party that we're not aware of?
I think there's a party here.
Okay.
I think a lot of people couldn't find parking spaces.
Well, you think so?
Well,
Okay.
I know of an example of someone that couldn't find
Okay.
a parking space today.
Or maybe they're afraid of the next storm. It is back to back, I guess, so they may be preparing again, right? So, anyways, this time it looks like we're getting some snow, so let's see. All right. Any questions from anyone before we start or anything? So pretty much today we're gonna talk. Remember when we saw our, I should have somewhere here, but our plan on the syllabus, we started always with the linear algebra basics, which you do, and you did it actually already. We discussed about the state space presentation of systems. So there is one more thing left, which is actually dynamic systems with noisy inputs, before we start developing the actual Kalman filter theory in the background. And I just pulled down and added on my notebook pledge notes. I think it's going to make us move a bit faster because this way, and I'm going to use this or this orientation, so I have enough space right here to write extra comments, and at least we have some structure to follow instead of writing everything from scratch. Okay, so what do we have over here? We know that our goal is to develop a Kalman filter, right? As actually the notes over here. And we want to pretty much do what? We want to estimate the internal state of a dynamic system, a hidden state as we call it, because we assume we cannot directly measure it, right? We have to estimate it. When we do what? When we measure values of the input and the output of the system, and we use one of these state space models we just actually derived in the previous chapter, okay? However, in most of the real systems, it's not that simple, mainly because, as you can see here on this nice figure, your system, apart from your input actually W, I'm sorry, which is missing over here, it also has actually disturbances, right? There is a disturbance actually in the input, and there is also sensor noise. Remember, I have a system, x of t, I can describe it in a state space format. I have an input and the output, and pretty much I can measure actually the input and the output. And through this state over here, I can make now, through the state equations, I can make some educated guesses, estimates about this state. However, in practice, most of the systems, the input here and the sensor measurement, they are both affected by noise, okay? Which means that no matter what I measure here and here, these measurements are not really clean measurements unaffected by noise. I cannot take them as super accurate measurements. So that's why this chapter is called Dynamic Systems with Noisy Inputs, because pretty much we have to consider that in the systems actually we are using these filters, there is noise in the inputs of the system and also on the sensors, on the measurement. So before we start delivering now the Kalman filters, we need to see how we can actually incorporate this noise both in the input and also on the sensing side of the system. All right? I hope that's clear. All right, so some things here to consider. First of all, by definition, noise is not deterministic, okay? It is random in some sense. In other words, we don't really know how noise is going to evolve over time. All right, it doesn't take particular values. It is completely random in nature. I guess most of you have done some courses, some background in probability and statistics. So this chapter is going to be mostly on that aspects, probability and statistics. But pretty much, if we want to discuss the impact of noise on the system dynamics, we pretty much use the concept of a random variable. Okay? Have you all actually heard the concept of a random variable? So a random variable, it is pretty much the result of a random experiment. Whenever actually you do an experiment, you can assign the result of this experiment as a random variable. This random variable must have actually a value. Let me write this here. So it must have a value. And we cannot actually predict exactly what we get each time we measure or sample the random variable, but we can characterize the probability of each sample value by the probability density function. Okay? The most typical example I guess you have seen in most textbooks about probability is either the die example. I have a die that has actually 6 sides, right? And I roll actually the die and I can get 1, 2, 3, 4, 5, 6. I have 3 actually options, okay? And if it is actually a fair and truly random die, I know that all these probabilities between the outcomes are actually equal, right? I have 1/6 probability to get any out of these numbers. Or the other typical example we are using a lot of times is actually the coin, that we flip a coin. And if we see the coin as a random variable, a random experiment, we just flip it and we have equal, quote unquote, probabilities for the outcome to be either actually heads or tails. And as I said before, in the case of the coin, we pretty much have to assign a value in order to mathematically model this random variable. So, I don't know, I mean, someone can assign heads as 1 and tails as 0, something like that, okay? So the outcome of the random actually variable coin, flip a coin, is going to be either 0 or 1, so head actually or tail. Okay, so I can perform actually this experiment many times, as you know. The outcome is completely random, as we know. So how I'm going to actually approach this problem? We use, as I briefly mentioned, let me make this yellow. We use the so-called probability density function, or PDF. Okay, there is a confusion in the literature, in the textbooks. You can find small case PDF capital PDF, and there is not only probability density function, there is also a probability distribution function. So some people, they use the capital one for the second one or whatever. Here, since I'm using these nodes, I mean, we're going to use the lowercase one, and it always corresponds to the so-called probability density function. What is a probability density function? First of all, in general, we denote probability density function PDF of a random variable x as fx of x. Okay, let's see that. So it is actually a function. We declare it like that, so we know it's a probability density function of the random variable x. So this internal actually x is a capital X. All right. And pretty much, as you can see here on the figure, pretty much we are talking actually about probability density. In other words, we see how actually the probability of the outcome for this random variable, it is distributed. All right? In general, if we have one of the outcomes, so let's say one of the outcomes of this thing here is going to be x naught, the f of x, the probability density function of the outcome x naught dx, it's pretty much, yeah, I know, it's going to come back, yeah, it's going to be pretty much a value between x naught and x naught plus dx. Okay, in other words, you know that I can have a distribution like that, a density function like that, and pretty much if I want to calculate now specific probabilities, I have to go and integrate between two different positions. So the probability of x naught, it is pretty much measured between x naught and x naught plus dx, wherever this dx becomes very, 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 very tiny. Okay, because in practice, what this thing actually here, it is being calculated most of the times. We are talking about the probability of x being between two values, let's say x naught and x1, and by definition this thing here, it is actually this integral. So I integrate from x naught to x1 this probability density function. Okay, technically there is no definition for probability of a specific element of the function. So for example, the probability of x naught, it is pretty much 0, right? Because I mean you have infinite points within the probability density function, but pretty much what we do in these cases is that we calculate the relative likelihood of all outcomes. Okay, so let's say if you want to calculate the outcome, I don't know, from here to here, you just pretty much integrate, calculate the integral of this area. And based on that, we also get, not sure what's wrong here, I may push something. We get we get, as I said, the integral of the area we are interested to identify. As you guess, this is just a function. There are actually some metrics that we use, and we're going to be discussing as we move on. But pretty much, maybe, I guess you have all done, again, probability statistics. Maybe you have seen the mode function of a probability density function, which is pretty much the highest value you can get on this probability density function, right? And there are even more. You have seen, I mean, the mean, the standard deviation, variance, things like that. We're going to see them shortly as well to see how this thing actually distributes. All right, let's talk about some properties. The first one is, these are properties that are true for all PDFs. The first one is the probability density function for every x, it is always greater than 0 or equal to 0. Okay, we know that, I guess, the probability, we cannot really have a negative actually probability, right? Always this thing actually here is greater than 0, so even when I integrate anything here, all these areas are greater than 0. Second, if I integrate the whole area below this curve, okay, in that case, the answer, the probability I get is 1. All right? So, for example, what is the probability if I roll a die to get an outcome that it is either 1, 2, 3, 4, 5, and 6? It's 1. Because definitely I know that this die is going to actually sit in one of these 6 actually areas, right? So if I integrate the whole actually area of the outcomes, the probability is 1. And the third one, it is actually something that we call the cumulative distribution function, where pretty much here it says that what is the probability of your random variable x to get a value less than equal of a defined x naught, then pretty much as we know, this guy it is equal from the integral. Let me do that again because it is actually the integral from minus infinity from that side up to the value x naught. So pretty much we are talking about all this area inside here. Okay, so the cumulative distribution function is starting from the lowest actually outcome, integrated the whole area. I'm getting the CDF for this particular PDF. All right. Any questions on that? Is there anyone who doesn't know anything about random variables and PDFs? We're going to use them a lot, but we're going to use actually the things we're going to discuss shortly. So the problem over here, and that's why we're going to find the other metrics we're using, is that apart from very simple examples, okay, it is often impossible to determine the probability density function. Okay, so pretty much we use approximations to capture the key behavior of this random variable, and for that reason we need to define key characteristics of this PDF. All right, imagine actually noise. Noise it is actually random. Most of the times, I mean, you cannot really model it precisely, even though we will assume that it is modeled as a specific distribution that we will see shortly. Most of the times it cannot really be measured precisely. You cannot really model as a precise PDF. So the problem here is that it is difficult to find this f of x, which means you cannot really use it, okay, to do analytical calculations for that. For that reason, we are going to use actually a few other parameters that they are super useful and make our life easier, because even if we had the PDF of all processes, most of the times it is really hard to go and solve this integral up here and get an answer. All right, the first one, and one of the most important ones, expectation. Okay, what is the expectation? The expectation pretty much describes the expected outcome of a random trial. Okay, so as you see here, the expectation, first of all, we denote expectation with x bar, and this is equal to this capital E, calligraphic E of x. Okay, this is here small x, so it is actually small x bar equals to the expected value of capital X, where capital X is the random variable. Okay, and this guy here, it is equal to pretty much the integral from minus infinity to infinity of x times f of x. Okay, let me write that one more time. X fx of x dx. Let's see what is this over here. So imagine, as I said before, if I have this PDF, the mode, it is actually the maximum number I can get over here, the highest actually f of x. Okay, the expected value though, it's not like that. If you see the expected value, it multiplies actually every outcome with the distribution function, and pretty much creates an average or a mean, as we call it. Okay, so imagine this thing here is like, I mean, a balance or something, and I want to find where exactly this actually is being balanced as a weight balance or whatever. So the expected value for this specific here PDF would be somewhere over here. As an operator, it is actually a linear operator, so it is very important actually to working with it, which means that pretty much we can actually do a lot of calculations as a linear operator. For example, the first moment about the mean, so expectation, it is pretty much the first moment about the mean, it is equal to the expected value of a random variable x minus the expected value of x, it is equal to 0, right? Pretty much this is easy to prove, because this guy, I mean, the expectation is a linear operator. This guy here, it is equal to e of x minus e of x bar. All right, but e of x, it is expectation value. We know it is actually x bar from here, right? X bar, now this guy here is a scalar, is a number, right? The expected value. What is the expected value of a scalar? It is the same scalar number again, okay? So this guy becomes x bar again, and this whole thing now becomes 0. Okay? So, expectation describes the expected outcome of a random trial. It is denoted with this x bar, and it is actually a linear operator. That's the thing to remember for now. Later on we will see why this is important, mainly because it's really hard to work analytically with the PDFs, but we can work actually with the expected values of the PDF. Okay? Just to give you a very abstract example, if you have actually noise in your system and you cannot really model it because you don't know the probability density function of noise, you can still make actually some calculations based on the expected values of the noise. In other words, how the noise now affects your system. All right, let's move on. Let's talk about the statistical average. So the statistical average, it is different from expectation, okay? And it is important actually we understand that, because sometimes expectation, we think it is actually the average value, but it's not the same with the statistical average. Consider a discrete random variable x that can actually take n values, x1, x2, up to xn. Then define the average by making many measurements. So what we do is we just do the experiment infinite times, okay? And then if we get, for example, mi is the number of times where we get as an output of the measurement I, then the statistical average pretty much averages all the outputs, okay? If that was a die and I have 6 outputs, right, and I actually throw, this die 1 million times, I would pretty much now, what my statistical average would be, 1 over n would be the number I did the experiment, which is actually 1 million times, right, times m1, how many times I got the output 1 from the die, times 1, plus how many times I got the output 2, plus 2, plus how many times I got the output 3 plus 3, etc. And I create now the statistical average of all outcomes. In the limit, this ratio here, m1 over n, which pretty much describes now the individual probabilities, in the limit, this thing over here approaches actually the expected value, okay? The notes here say, assuming ergodicity. Does anyone remember or knows what is ergodicity? Have you ever heard about ergodicity? So we have a random variable, right? which represents a random process. Ergodicity means that this process does not really change over time. So if I started my experiment with a die which was perfectly balanced and the outcome is truly random, if I throw it 1 million times, I don't change somehow its geometry or mass or whatever, so suddenly it starts now outputting more sixes as an output compared to threes, for example. Okay, so pretty much this guy here means that, let me write it down so we have it. This guy here means that the process doesn't change over time. All right. So statistical here means that it can converge to the expectation in the limits. Okay. We could show the same thing for continuous random variables, not now of course, but pretty much statistical can converge to expectation in the limits. To give you pretty much an idea of the difference, what is the difference between the statistical form and the probabilistic form, which now approaches the expected value? Have you ever considered what is the difference between probability and statistics? I mean, why we at least name them as two separate things and sometimes treat them as separate things? What is the difference of probability and statistics?
Probability is a very specific portion of statistics, and statistics is very wide range.
Okay, so you say that one of the my probability is a subset of statistics.
Yeah.
Okay. I'm not sure I agree with that, but let's figure it out. Okay. Is there something different? I'm sorry?
The statistical is something, you know, you are sure about the results somehow. But probability you are not sure. You have to guess, you have to estimate.
While statistics is what?
We are sure about the results.
Oh, okay. So in statistics we are sure about the results, in probability we are not. Okay.
Yes.
You are getting closer. Okay. So think about it. So it's not really a subset or sure about the results, but you are very close, both of you. The idea is the following. I have a random process, right? I run an experiment that may bring out a random outcome. I roll a die. I flip a coin. Okay? When I say that the probability of flipping a coin and getting heads is 50%, assuming of course again I have a fair coin, this means that I calculate the chances of this outcome without having really to flip the coin. So this is my calculation, my estimation before I even do the experiment, right? What is statistics? Statistics is I'm gonna flip the coin 1 million times and I'm gonna verify now that all the outcomes, they were quote unquote equal. So I got almost equal number of times heads and tails. So if I flip the coin 1 million times, okay, and my statistics show that I got 500,000 times on heads and tails, I would say the statistics of this experiment were 50% heads, 50% tails. Okay, and this would verify now my claim that initially I thought that both of these actually had exactly the same probability. Okay, if somehow I guess as an output on the statistics that heads came out, I don't know, 200,000 times and tails 800,000 times, then there is something wrong on my process. It's not a random process anymore, or with my coin. But what I try to say here, which is not always easy to realize, is that the difference between probability and statistics is that probability does not even require an experiment. Okay? In order to make your guess, you don't even require an experiment. You just calculate the probability of an output to happen from an experiment. Statistics is do this experiment many times and try now to run the statistics or pretty much show the distribution of the outcomes over time. So pretty much the difference over here, and that's why these two things are equal in the limit and only in the limit. Expectation, it is pretty much what I expect to come out of the random experiment, while actually the statistical average is that I do the experiment for a lot of times, and in the limit I expect both of them to be equal. All right? So imagine this thing that I have a random input, right? For example, I run a process and I cannot really measure the noise. Okay, I cannot actually measure the probability density function of the noise. Or typical systems that you cannot really model is actually the wind. You do an experiment outside and there is wind and you don't know how to model actually the wind, all right? The idea over here is that even if I don't know this density function, how I can use the expected value, the expectation, to build my my system, the discussion for my system development. All right. Any questions on that, guys? Is that clear? So the next thing that you probably also know, it is actually the variance, okay? The variance, it is actually the second moment about the mean. So the first moment about the mean was expectation, remember. The second moment actually about the mean, it is actually the variance. How is the variance here defined? It is pretty much the expected value of what of my random variable minus the expected value, okay? And all that is squared. You have to solve this integral as you see here, but all this guy pretty much becomes the expected value of the squared random variable minus the square expected value. Okay, so it is equal to the mean square minus the square mean. What does this thing actually say here? So what is my second moment about the mean? Pretty much says how far away is an outcome from the mean value. Okay, so remember what we call actually a variance. I have actually a random experiment. I have an expected value, which is actually the value I expect to come out, but I also provide a variance that shows me how far away is an outcome from the mean value. So pretty much the statistical average we saw before gives the central measurement of the probability density function we discussed, while the variance shows how wide the probability density function is. Okay, so, and we're going to see this with the next thing, which is the standard deviation. But imagine you have one distribution like that and one distribution like that. Okay, not the best plot, and we're going to see more on standard deviation, but pretty much both of them, they have almost the same expected value, but the second one has a much wider variance, so I still get a lot of values which are far away from my expected value. A better tool for that, it is actually the standard deviation. The standard deviation, it is a measure of the dispersion about the mean of the samples, and it is defined as what? As the square root of the variance. Okay? So in other words, it is another indication of how wide actually the distribution is. The question is why it's useful. I mean, if we already have the variance. As you see these two equations here, do you see any difference between them, between the variance? I mean, with the standard deviation being the square root of the variance, do we get any benefits? Have you ever considered why we use standard deviation? I mean, when you write actually a distribution, right? Most of the times you write actually the expected value and you also write down the variance, right? The standard deviation, I'm sorry. Well, the reason is that, take a look at here. This guy, the standard deviation, has the same units with the expected value. Right? So while both of them, they show the dispersion of the probability density function around the expected value, one of them actually is squared, so it doesn't provide the same units on these actually measurements, right? While the standard deviation, it is expressed in the same units of the variable. That's why it is much more useful than the variance. We're going to use them, I mean, both of them. I mean, they are connected either way. So the important thing here always to remember is that the standard deviation, it is the square root of the variance, okay? So the thing to remember here is that you will see this thing written like that. Okay, so the variance, we will write it down as sigma x squared. The standard deviation, we will write it down as sigma x. All right? Something here to understand the variance. This is the Chebyshev inequality. I think the explanation is probably a little bit complicated, but let's see at least the inequality. Pretty much the Chebyshev inequality says what? That for any positive epsilon, the probability of x minus the mean value to be greater or equal than epsilon, it is less than equal to what? To the variance over epsilon squared. Okay? In other words, this implies that the probability is concentrated about the mean. Again, same example like I did before, and I have two distributions. I have, wait, that's super wide. I have something like that, and I have the second one, which is super wide like that. All right. The standard deviation tells you how certain you are about the outcome of the experiment before you get it, but you have two functions here where while you have exactly the same mean or expected value, these guys here, they have different actually deviations, okay, standard deviations. I hope you remember also, for example, that in these systems we actually calculate what is actually the difference between one standard deviation, two standard deviations, three standard deviations, etc., right? So pretty much we get to systems where we try now to predict, the distribution function predicts the outcomes of the experiments, how close they are to the expected value, all right? As we will see soon with one of the most widely used distributions, actually let's take a look very quickly here. We're talking about the Gaussian normal distribution. Within three standard deviations here, we get 99.7% of the outcomes. It's very rare we get something outside of this limit. So pretty much this inequality here, the Chebyshev inequality, shows that the probability, it is actually clustered, concentrated around the mean, and that the variance, it is an indication of the dispersion of the PDF. So it is variance that informs us how uncertain we are about the value of a random variable. Okay? This is the important thing to remember, practical advice. Low variance means that we are very certain about the value of the random variable, while high variance means that we are very uncertain about its value. Okay? Soon we will see the covariance, which is something similar, but it talks now about we will soon jump from one random variable to a vector of random variables, and in this case we're going to be talking about covariances. Alright? So, thing to remember, we have a random variable. This random variable, we do care about the probability density function. In other words, how the outcomes of this variable they distribute in this function, and we will focus mostly on the expected value of this specific distribution function, the variance and the standard deviation, and later on we're going to talk about the covariance. And the idea over here is that low variance means we are very certain of its value, high variance means that we are very uncertain of its value. Alright? Any questions, guys? So let's try and think about it a little bit. For the example I gave you before with the die, okay, what kind of distribution you expect to get? Is this something like that? Where the output is actually concentrated about the expected value? Or you think that it is something more wide, where pretty much I can have almost equal outcomes? So remember, on this specific example, I expect to have a fair actually die, right? So I would expect all the outcomes to be almost equal. So it's one of the most difficult things to model actually, but in that case, I don't expect to have, a very close variance on my distribution. The expected value, it is actually 3.5, exactly the middle, right? But my variance, it's actually quite wide, because I expect to get anything from 1 to 6 regularly, many times, once I actually roll the die. Okay? So it is actually a very wide distribution in this particular example. All right. Gaussian. Is there someone who has never heard about Gaussian? This is probably the most well-known thing. I mean, I guess everyone knows actually about Gaussian. So this is the most important distribution we will use in this course. Okay? So we need to make sure we understand how exactly it works, how it is related to what we discuss over here. We will see later on, of course, why it is so important, but it is one of the most well-known distributions. So it is called a Gaussian or normal distribution. Its probability density function, it is defined like this guy over here, okay? So fx of x, it is equal to 1 over square root 2 pi times sigma x times actually remember, sigma x is the variance, sigma x is the standard deviation, sigma x squared is the variance. Standard deviation times the exponential of x minus x mean expected value of x squared over 2 times the variance. What are these properties of this one? It is actually symmetric about the expected value. You can see here on this figure pretty much multiple Gaussians in this plot, where pretty much you see that these guys, they have exactly the same expected value, so their mean value, it is actually 0. Let me write that. And they are symmetric about 0, while their peak, it is actually proportional to 1 over sigma x at x of x, so this guy over here. How we notate this thing? That's the important thing. We notate it always like that, so pretty much we say, let me write this down, that x is a random variable, that it is distributed, so when you see this tilde here, this wiggly symbol, it is distributed with normal, so that's why we use this n, the calligraphic n, or Gaussian, but we use the n from normal, with what? With a mean x bar and variance sigma x squared. Okay, so when someone wants you to use a Gaussian distribution, they will probably give you something like that. You all do research, so probably you have seen it in papers. You see people saying, I'm using a random variable, and they provide these symbols over here. This thing means that what? This capital X is a random variable that it is actually distributed with the normal or Gaussian distribution, with mean actually x bar and variance sigma x squared. Okay? The probability that x is within sigma of x, one standard deviation, it is actually 68%. Okay? In other words, the outcomes are quite concentrated within one standard deviation. The probability that x is going to be within 2 standard deviations is 96%. And as I said before, the probability that x is within 3 standard deviations, it is 99.7%. Which means that if you have a process that it is modeled with a Gaussian distribution, it means that within 3 standard deviations, you have most of the outcomes actually covered. They will fall within 3 standard deviations. Okay? In other words, a 3 standard deviation range almost certainly covers observed samples. All right? Have you heard again, guys, about the standard deviations, about distributions within 1 standard deviation, 2 standard deviation, etc.? This is widely known, especially, I mean, when you try to provide distributions, probability density functions, it is very widely used to include the outcomes, to provide how the outcomes of a random actually process are distributed about the mean value. All right? Probably one of the most well-known things, I don't know if you have heard it, is actually not 1 or 2 or 3, it's actually 6 sigma. There are actually even 6 sigma manufacturing processes, which pretty much you want to make sure that through the manufacturing process, you have the quality where all your outcomes, your products, they fall within 6 sigma of your mean value of your process. Okay? All right. In general, a narrow distribution is going to have a sharp peak. I guess you all understand that. Let me do that one more time. So pretty much, again, if I have this guy here, a very sharp peak, it means I have a very high confidence in predicting x. Again, here in that case, my 1 sigma is going to be here, my 2 sigma is going to be here, and my 3 sigma is going to be somewhere here. All right? While if I have a wide distribution, so imagine something like that, all right? Then in that case, my 1 sigma is going to be here, the 2 sigma here, 3 sigma here, etc. It makes wider. In practice, this means that I don't really have a very good knowledge in what to expect actually for x. All right? Any questions, guys? So let's write this over here so we have it also as noted. X here, the expected value of capital X, it is my X bar, which is this guy up here, while this guy over here is the variance of X. Okay? Any questions? Have you ever played with Gaussians? Sometimes? Okay. It's not the easiest one. I mean, most distributions are not the easiest ones, but the good news over here is that we will not really need to use directly the PDF. That would make things more difficult, right? So just to give you a little bit of insight why we use them here, and what is this key importance of Kalman filters, there are two reasons I think why Gaussians are very important in this application. The first one is, as I said before, you have a noise which is random, right? And most processes, they are affected by random noise. However, it turns out that a Gaussian distribution, it is a very good approach of the noise distribution. So in most of the applications, we assume that the noises are following the Gaussian distribution. Okay? They are random, they have this format. Even if they don't perfectly fall under the Gaussian umbrella, it is still a very good approximation. The second reason that we will see it hopefully today is I can work very well with the Gaussian distribution without having to play with the PDF, just by managing the expected value and the variance. And when it gets to the point that I need now to add distributions or create combinations of distributions, the Gaussian distributions, they have super important properties that they make our life much easier. All right? Let's move on, and again, we're gonna see it actually shortly. All right. The next one is about vector random variables. All right, we discussed about a single random variable. Okay, I have a single coin and I just flip it. Imagine now that I can now create and manage vectors of random variables. So now my capital X, it is a vector of different random variables. Okay, so someone would say that I would just run two experiments in parallel. At the same time I'm rolling a die, I'm going to flip a coin. What are actually the outcomes of these experiments? So in this case, pretty much I have a vector of random variables and I do n random experiments that I organize in a vector. The capital X is the random variable, as I said before. The lowercase x, it is actually a number, it is the outcome of each one of the random variables, okay? So this thing is as simple as take one random variable, actually many random variables, and put them inside a vector. In that case, remember, for one random variable, we used a PDF, a probability density function. For vector random variables, we use what we call the joint PDF fx of x of a vector x, where in that case, this fx of x0 means what will be the output of my random experiment in the case where my x1 it is equal to 1, x2 it is equal x2, etc. In other words, what is the probability, to give you an example, if my first random experiment is the coin, what is the probability of my coin coming out as heads and my die coming out as 6? Okay, this is one of the many outputs I can get on this distribution. Similar to before, this guy here, it is the probability that x is between x0 and x0 plus dx. Remember, we had something like that, and we said if we have x0 and this here is dx. Pretty much we have to integrate in order to get these probabilities. All right? What is the difference here? The difference is that now we have added one extra dimension because we have a vector of random variables. So while here we had actually in a single dimension probability density function, now we have it in 2 dimensions, something like, I don't know, something like that. Imagine an x, y, z. So I have distributions like that, and at the same time distributions like that, like small cones or ellipsoids or things like that. Properties of joint PDFs. First of all, the like before, the fx of x, it is always greater or equal than 0 for every x. That's the same like before. The second thing, it is also something similar like before. If I integrate all possible functions with all possible outcomes, the output is 1. So what is actually the total probability of all events happening? It is 1. Okay, so what is the probability of if I flip the coin and at the same time roll the die to get heads, tail, 1, 2, 3, 4, 5, 6, all the outcomes? It is 1, okay? The next one, it is about the expected value, which is also the same. So the x bar, it is the expected value of this thing. Remember that this thing over here, it is a vector, which means that this guy is here as a vectors as well. So pretty much we're talking now about the expected value of the overall vector. Okay, the next one is something new that we didn't see that before. So let's highlight it in a different thing. We have the so-called correlation matrix. Okay, what is the correlation matrix? The correlation matrix pretty much describes how one component tends to vary compared to another component. Okay, let's think about that. I have a vector of random variables. Okay, are these random variables correlated in some way? I can have 100,000 variables. I gave you an example only with 2. In one hand I have a coin, in the other hand I have a die. Okay, by flipping a coin and getting an output, is this somehow correlated with what output I will get if I flip, if I roll the die? Okay, or I hold the coin and someone of you is doing the same experiment with another coin. It doesn't have to be separate, but you do it across the street in the other main. If both of us we flip actually the coins, okay, are these two experiments correlated somehow? Okay, I don't know if some of you have ever heard about this chaos theory and the connection of things, how correlated they are in this world, right? And the flip of a butterfly in the Amazon that affects now the climates in the rest of the planet, right? All this crazy theory. But the idea here is about correlation, okay? In other words, how one PDF for one of the elements of the vector, if it correlates to another one. They may be dependent linearly, or so they both increase at the same time or decrease at the same time, or the opposite, or they may be completely uncorrelated. But pretty much we are talking about this guy here. This guy here, so let me write it down so we have it clear. The correlation matrix, it is what? It is sigma x. It is defined as the expected value of x times x transpose. So I take my vector of random variables, I multiply with this with the transpose, and this now gives me, I take the expected value of that, and this gives me the correlation matrix. By the way, this guy over here, it is, do I have it here? Yeah, we call this a matrix. Okay, Why? Because I take the expected value of these two things. What are these things? These things are vectors. But remember, the vector of the random variables is by default a column vector multiplied, or as we say here, outer product with the transpose, which makes it now a row vector. The outcome, it is now a correlation matrix. Okay? So remember, the correlation matrix here, it is the expected value of this thing time actually itself. This is different than what we saw in a single variable with the variance and how this is defined about the mean. The second thing here that we will use a lot, much more than correlation, is covariance matrix. Okay? And the covariance matrix, it is actually defined as x tilde minus x mean. Actually, the covariance is this guy down here. It is sigma, so covariance, it is sigma x tilde. It is defined as what? As the expected value of this guy over here, x minus x bar times x minus x bar transpose. So, by definition, we see here that what? This x tilde, it is pretty much the difference between some variable and its mean. Okay? Remember, this here is a vector. So what is the difference between the x variable and its mean? And if I take the expected value of this difference, we get actually the covariance. All right? A covariance of a vector is a matrix, like before, and pretty much the connection here that we will see is since I defined x tilde like that, if I take the correlation of x tilde, what do I have here? I have the expected value based on this guy up here, so I replace with x tilde here, which is x tilde times x tilde transpose, and this guy it is equal to the expected value x minus x times x minus x transpose, and this is how I end up with the covariance matrix. Okay, the covariance matrix is a symmetric and positive semi-definite or PSD matrix. Okay, anyone remember what does actually positive semi-definite means? It means that all eigenvalues are non-negative. They could be zero, but definitely they cannot be negative. Okay, that's by definition something we need to remember about the covariance matrix. Why this is useful? Because this means that for every y, for every actually column vector y, this property holds true. Okay, pre-multiplying with the y transpose and post-multiplying with y, the outcome, it is always greater than 0. All right? Pretty much what we have here is, since my covariance matrix it's something like that, this is symmetric, as I said before, and the main elements of the main diagonal, they are pretty much the variances of each one of the random variables inside. Okay, we have this little proof here. I mean, you can see it. I'm not gonna spend some time on that. But why this thing it is important? Because this allows us to notice that correlation and covariance are the same for zero mean random vectors. All right. The covariance entries, they have a specific meaning. So the ones on the main diagonal, as I told you before, they are pretty much equal to the variance of each one of the processes, of the random processes, while the other elements over here, they can be provided, I mean, they create a symmetric matrix around the main diagonal. So the diagonal entries are the variances of each vector component, and the correlation coefficient, which we have over here, it is pretty much a measure of a linear dependence between xi and xj. In other words, we have information about correlation inside this covariance matrix. Any questions, guys? We will not use that much correlation, but covariance is going to be a major component in the Kalman filter, as we will see later on. So the important thing over here, I guess, is to remember how exactly it is defined and what exactly does it mean, right? So how actually we have a difference variance between the elements. Yes, go ahead.
The correlation matrix is for only one vector of the random variables or two vectors on random variables. Each we are doing the correlation for one or for two different vector variables, the random variables. If I just say two, we have two variables, yes?
You have a vector of random variables, so you can do it for many.
Yeah, for example, we have many cases, many incidents we are trying to measure, yes, the happening of that incidence. So we have two here, right? Two different incidents. One you said here, another one the main S3. So when you use the one same X vector with the correlation matrix.
These guys here are vectors, not random variables.
One random variable.
No, you have many inside. You can have many.
So
If you use one, you get pretty much what we discussed on the single random variable before, but you have many, okay? And so let's say you have a system that has 5 random variables. X is actually has a length of 5, okay? However, when you create a correlation matrix, it is the product of X times X transpose. If you multiply this is going to end up actually with a matrix.
So the X is the.
But why you need this matrix? This is the question, I guess, that you try to understand. If now I have 5 different random variables.
5 different incidents.
Not incidents. Incident, you mean outcomes, right?
Process. Measurement.
But they are different.
Different position, different status and values. Yeah.
So in that case, for example, before I gave you an example with 2, the dice and the coin.
Yeah.
Or we could all have a coin over here. I mean, we are 10 people and we have 10 coins. And we flip 10 coins. Yeah. All these 10 are different, as you said. 10 different instances, right? So if we create a random variable vector, it's going to have x1, x2, x3, x4 inside. Each one of them being one of our coins, okay? If you multiply this with the vector, you will get a matrix. Now the question is, why do you care about this matrix? Because the real problem is that if you have these 10 different instances, you want to see if there is a connection between them. So we flip all the coins together. Is there a connection of the outcome of my coin with your flipping of your coin? In the example you measured before, you said, I don't know, position, velocity, or whatever, right? Is the outcome of your position measurement somehow affecting your velocity? And you want all this to be included in one matrix that we call it correlation, because that's the only way over time as the system builds and you update the correlation covariance matrices, you can see over time if one of the random processes affect the other. We're going to see it shortly, I think so, because we don't have much time, but actually I think it's here on the next one. Let me quickly show. That's a great question. Look at here what we're going to study next. Uncorrelated versus independent. So what do we care over here by building these matrices? We do care about if these processes you just described, if they have correlation or dependence. So we're going to actually separate correlation and dependence. We're going to have two cases, if they are uncorrelated and independent. And as we will figure it out, one of them is a much stronger condition than the other. What I mean is the following. If two joint PDFs are actually independent, then they are also uncorrelated. But the other one is not always true. So there may be not correlation between two instances, but this doesn't mean that they are not independent. Exactly. Exactly. Because these things are connected, right? This is exactly what we're going to see next. Okay, that was a great question. Okay, let me go back quickly to finish this. So, similar to before, we can take the single random variable Gaussian and extend it to the most important multivariable distribution. Okay, so this is the multivariable Gaussian, and this is super important for Kalman filtering. This is actually what we're going to be using from now on. So take a look here. Let's avoid the huge proofs over here. But what do I have? I have fx of x. It is equal to this guy over here times this guy over here. Okay, where sigma x tilde, it is pretty much this guy symbol here. It is the determinant of sigma x tilde. Again, remember, sigma x tilde, it is my covariance matrix. Okay, so and because I have this guy here inverse, I have the inverse of a covariance matrix. This actually distribution requires that the covariance matrix, it is positive, definite, as I said before. The notation in this case, it is this guy here, okay, and the contours of these guys are hyperellipsoids that they are centered around T. So pretty much if you see this from the top, this guy here, okay, you could have things like that, right? Before we see the two-dimensional case, let me see something here. I think Gaussian. Copy. I intentionally want to copy the So this is the one we saw before, all right? This is actually the single PDF for the Gaussian. This is the multivariable one. So pay attention to that. It definitely looks like a Gaussian, all right? So try to start memorizing a little bit about the format, right? So this thing 1 here over square 2 pi times sigma x, etc. What is happening over here? Here you have actually your covariance matrix, right? In case where you have a single variable, you don't really have a covariance matrix, you have a scalar here. This is actually a square root. So what do you get over here? You get, this is actually n is the number of your random variables. If you have a single random variable, this guy here is 1 over 2. So this guy here, it is 1 over square root of 2 pi. This guy here now, because we don't have a covariance matrix anymore, this now becomes what? It becomes your variance. Okay? So it becomes your sigma x. The same actually applies over here. So we're talking actually about the same distribution in multiple actually dimensions right now, in more dimensions. And we have the case of two dimensions. We call this a two-dimensional Gaussian, 2D Gaussian, where pretty much you see that in that case, whenever I have my covariances like that over my variances like that over here, I have a simpler covariance matrix, and this how distributes on the Gaussian. All right, I don't want to run super late because we're also recording here, but pretty much the idea over here is start memorizing a little bit the PDF for the multivariable Gaussian. And because it is complicated, it's going to get even more complicated. We will not really use it as is because it's really hard to solve it, but we are going to keep using things that we can handle, like these two things here, guys. Expected value and covariance. The good thing about the Gaussian, as we will see shortly, next time actually, is that I can use these two things, and these two things fully describe the whole PDF. I don't have to worry about the rest of the math. Questions? No? Okay, sorry for running 1 minute late. Thank you very much. Stay safe over this storm. I think the likelihood, since we're talking about probabilities for this storm, is higher than the previous one. But let's find out, right? So